Hey guys, welcome back to another episode of Intelligence Maxin. So, what I want to do here is I have an exam coming up for my computer architecture class, and I'm going to try to spend some time going over practice problems. So, not homework 1, but problem set 1. So, I think let's just get right into it, right? The first one here is when parallelizing an application, the actual speed up of speeding up by the number of processor. This is limited by two things: percentage of the application that can be parallelized and the cost of communication. Really? So I remember Amdahl's law. You have, let's actually do, so Amdahl's law. Right, so this is kind of defining the speed up of a processor is equal to 1 by 1 minus, call this the portion of an application that can be parallelized. So I'll call it F, and right, so we have SF. Right, because this F here is going to be a number between 0 and 1. And the speed up then is, okay, well, actually let's think about this. So I think you can think about this as old time, new time, right? So this is equal to, essentially your old time is the portion of our application that can be parallelized, which is F. This is 80% plus the speed up, or I guess the amount of time our application has been processed. Because in this case, S is the number of processors. Because maybe you're essentially doubling. If you have one processor, so do you need more processors to actually speed things up, or can you parallelize an application within a single processor? I think what we could do here is we could do, this could just be 0.2 plus n number of processors divided by 0.8. I think this could be possible, right? Communication. I'm cooked. Yeah, this is actually pretty hard. Because I don't know where the number of processors here. Maybe it's like n times this. So yeah, s, and then we have n times Dawes law, the speed up. Oh, you know what? I think this could be, instead of that, it could be this. Because essentially this is sort of the amount of execution time that is reduced, S. I think it's maybe 1%, but you could have the number of processes here, n times S. So you kind of get this number of times, or a factor of how much the actual execution time is reduced on the parallelizable process. Okay. I think I can keep it here as a percent, so 0.005. Yeah. So I think this is probably what we'll get then. So 1, we have 0.2 plus, in this case, have 8 times 0.005, right? So that'll be, oh, no, we want. And I think it'll be 0.8. Alright, so let's think about what this actually gives you. In this case we have 1 here. If we divide it by a decimal, then this is a gross. So the speed up would be greater than 1. I think if if the number I think I actually might have this backwards. Because I'm trying to think in my head, alright, you have this really, really, really high amount of speed up. So as S goes into infinity, what's going to happen? Speed up's the wrong word, I keep saying it, but if you sort of, I don't know what S is, yeah. Shoot, okay. Mean time till failure, I totally forgot how to do this. But let's try it. So this one to come back to kind of hard. Okay. Mean time to failure. I forgot what FIT stands for. I'm not gonna lie. Okay. So what does FIT mean? Failure in time, maybe? How does mean time to failure relate to failure in time? Okay, so assume that a 100 processor system is built using processor above. It takes 30 days to get this system. Oh shoot, I forgot how to calculate availability too. Availability. Okay. I think this is maybe doable. Let's see. Slash code. Put this in C. Copy. Oh shoot. $64-bit integers. All right. So LD, SD, I guess these are load double, store double. Load double word. Load word. Oh man, I hope I don't have to memorize all of these instructions, because I do not. Okay, so write MIPS code in assembly. Let's code this out. So what do we have to do here, right? We have to compare if A is greater than B, C is equal to negative. Alright, so let's load double word and throw this into register 1. And I think what we need to do is we actually need to access this memory address, so I think we could just straight hardcode this for A, B, and C. Yeah, I think if we do this, this is okay. If we want to store in, if we want to do hexadecimal, right? Oh shoot. Oh, come on. Okay, let's just do this first. So R2, we want a 0 offset 2008, and have 16. Okay. So this should store R. So A, call this B, and I don't know why there's always a dot. Oh, it's because I need these commas. Okay. And C. I think if I want to do hex, right? For 32, no, this is going to be a 64-bit address. No. I'm trying to think actually, right? I think all addresses are going to be 32-bit. Doesn't matter if you're storing a double word or single word. But I do think that your increment in addresses is going to be 8, so shoot, I forgot how to convert hex to, or base 10 to hex. I know with base 10 to binary, right, you could just straight up just use 0, 1, 2 and try to compute that number. Maybe it's the same thing with 16, so you have 16 or what if we converted it to binary, then to hex, right? Is that possible? So if we take 1,000, for example, let's see, so we have 0, so this is, I guess, that's 2, 4, 8, 16, 32, 64, 128, 256, 512, and 1024. Okay, so in this case, I think 2 to the 5th is 32, so 1, 2, 3, 4. It'll be 2 to the 9th, right? But we're going to have to keep adding these. So let's just start from the end. We have 1, 1, 1. So 512 plus 128. It's going to be, so 8 becomes 0. 2 plus 1 is 3, so 30. 30, we have, so it's 630. 630 plus 256. I guess we can add these two together. So we have 630 and 256 plus 64. Yeah, maybe a better way to do this is actually you take 1024 and you just keep subtracting. I think this, yeah, we're missing one here. It should be 1, 2 to 0, 2, 4. Okay. So 16 minus plus 8. So I think it'll be something like this then. So you have 1, 1, 0, 0, 32, 64. Oh, shoot. 1, 1. Let's see if we can keep this. Right. Okay, match the numbers. Alright. One and then, oh, so yeah, it's just that. So now that we have a binary number, can we convert this into hexadecimal? I'm trying to think. So this will combine into 1, right? Yeah, I don't know. I thought that would be an easier conversion, but having a hard time to be like 16 16 squared, it's already a pretty high number. 16.3, yeah. To convert to hex. Okay, I'll save that for failure. So we've we loaded these double words into our registers, R1, R2, let's do R3. So once we have them, what we want to do then is we want the negative a plus b. Okay, so think range greater than call this less. So yeah, so if the value of A is greater than the value of B, then let's jump to less. Oh, right. Maybe if it's less than. BLT, jump to skip. No, it should still be less, right? So we don't want to do this. Should be skips. Confusing myself. Alright, skip. Alright, and then, okay. Do you have to go use the bathroom? And then actually I gotta start my office hours. So I'll probably come back to this soon. Alright, see you. Alright, thanks for tuning in. Catch you guys in the next one. Peace.